All right, so 3.1 log and natural log function attributes and transformations. Today is supposed to go a little quick because it's stuff that we should already be able to do and understand. Okay, so if I'm going too fast, then you are the ones to let me know. Hey, Miss Jones, I know I probably should remember this, but I actually don't. Okay. All right. Up first, we have log attributes of the given function when of the log function when b equals 2. Okay, so normally any log is log base b of x. In order to graph, b has to have a value. Okay, so we have graphed here is log base 2 of x. Okay, that's what we're analyzing, log base 2 of x. We're going to go through domain. What is the domain? Domain means you're doing what? Your x's, right? Going left to right. What are your x's doing left to right? Well, where do my x's start? They start at 0. Good job. And where do they end? Positive infinity. So my domain is from 0 to positive infinity. Or you can write it as x is greater than 0. Agree? All right. Range. What is my range doing? My up and down, right? Starting from the bottom to the top. What's happening? What's happening at the bottom? It's going on forever, right? So at the bottom is going on forever, and at the top is doing what? Going on forever. So we're from negative infinity to positive infinity, which means that it's all real numbers, right? All real numbers on the y. Next, your intercept. Where do you cross the x-axis at? We do. We don't cross the y-axis, but we do cross the x-axis at 1, 0. So I don't have an y-intercept, but I do have an x-intercept. And where is that x-intercept at? 1, 0. Okay? Asymptote. Is there an imaginary boundary line that's preventing my graph from going forever on the domain? Yeah. And where is that imaginary boundary line at? At 0, right? That's why we start at 0, right? So our imaginary boundary line is at x equals 0. Therefore, we have a vertical asymptote. I forgot the y in there. Go with it. At x equals 0. The last thing we want to talk about here, well, last attribute we're going to analyze is whether it's increasing or decreasing. We read graphs from left to right. So what is our graph doing? It is increasing over our domain. And our domain again is 0 to positive infinity. That's our domain, right? So it's increasing over our domain from 0 to infinity. Okay? Identifying attributes by now should be something you are comfortable with. Tell me the domain, the range, intercept, asymptotes, and whether my graph is increasing or decreasing. Okay? All right, next, we're going to talk about specific attributes of log functions, okay? Where your graph is, where y equals 1, that tells you your b value of the parent function. So notice here, this is at 2, 1. And what do you see? What is our b value? 2. Do we see that? Okay. Where your y equals 1 is telling you your b value. So if it had been at 4, then my b value would be 4. It would be log base 4 of x, okay? Remember, a log is asking you your base to what power makes your argument, right? So here, if I go here at 4, this is asking 4, 2 to what power makes 4? 2. That's why it's at 4, 2. If I go here, this is saying 2 to what power makes 8? 4. Count up where we're at 3, and that's 2 to the 3rd power makes 8. Okay, that's how you're reading the log graph. You're saying the base to what power makes the x, and the y is the answer to that. All right, got it? All right, so next we're going to change the value of our base, but do you think that's going to change our attributes? No. So notice here we changed our base to be 10. So now we have common log. Log base 10 of x is just log x, right? That's called our common log. It's the one that is on your calculator. It's if you press log, it assumes your base is 10. Okay. Now, looking at the graph, did our 5 attributes change? No, my domain is still from 0 to infinity. My range is still from negative infinity to positive infinity. My intercept is still at 1. My asymptote is still at x equals 0. And from left to right, the graph is still doing what? Increasing on my domain from 0 to infinity. The only thing that's going to change is how you're interacting with your x values. So we're still here at 1, 0, but notice we're now at 10, 1, and that's because what is our b value? 10. Okay? 10 to what power equals 10? 1. All right. So do we see the pattern in it? The base may change, the attributes are going to stay the same, but so will the value of, well, the x at y will change. That 1 will change, sorry. Okay, cool. Next, we're going to talk about our transformations. All right, we've done transformations all year long. Guess what? They're going to stay the same. Okay, so if you have a number that is being added to the log, so notice it's outside of the x, right? That is our vertical transformation. It's our vertical. So it's saying whether we're going up or down. If I'm adding, then we're going up. If I'm subtracting, then we're going down. Okay? If I have a number inside with x, that's our horizontal. And what do we need to remember about our x's? They're liars. Okay, so the key thing is, if it looks like I am subtracting, I'm actually going to the right. If it looks like I'm adding, I'm actually going to the left. Because it's going to look like it, but it doesn't actually mean that it's minus. So this is x minus a positive. So you're focused on the fact that c is actually a positive. So you're going to the right. Yeah? Okay. All right, next is our A, our stretch, compress, or reflection. Okay, A, focusing on A, not whether it's negative, but just focusing on A. If A is greater than 1, you have a vertical stretch. If A, the absolute value of A is between 0 and 1, then you have a vertical compression. When it's point something, it was 0.5, 1/3, 1/4, that would be a compression. Okay, now if A is less than 0, meaning that if A is negative, that's what's going to cause you to reflect. Okay, so I can be greater than 1 and negative, right? There you go. So if it was -4, I would be reflected and I would be a stretch. Yes. It's literally reflecting. So if I'm reflecting across the x-axis, so here am I currently, right? When I reflect across the x-axis, I'm now doing this to the best of my ability. Like I can't draw very well. You go. And then if it's going the other side, yes. So then if it was over, which we focus more on in pre-cal, it would be that way. Okay. So we don't focus a whole lot on y-axis reflection until pre-cal. All right. Okay.
Wait. In a table, in a x and y reflection,
Uh-huh.
it's going to change the x reflection. Why?
It's your y's, yes, because that's the only way you're gonna reflect over the x-axis. You're going
Okay.
from a positive y to a negative y, or from a negative y to a positive y.
Okay, and if it's reflecting against the y-axis, then
You're changing yours. Exactly. Perfect. All right. So we have two functions. We have y1 and we have y2. Y1 is log base 2 x plus 4. We're going to describe both. We're going to graph both. Okay. For graphing, if you want to draw in your axis, you're going to have, I would say, maybe go here for your x-axis and in the middle should be good for your y. All right, so we're gonna do y1 first. Y1, what is y1 telling me? What transformation variable am I using? It's horizontal. Good job. So we know it's C, but it looks like a +4, but it's actually a what? A -4, which means that we're going to the left. Okay. So in terms of what's happening here, if you look at our parent function for log base 2, we're taking that whole function and shifting it to the left. Does that make sense? Okay, so I'm going to pull some values from that so that we can see what the parent function looks like. Huh? Oh, it's left. Sorry. It just came merged together. All right, so on our parent function, if y'all flip over for me, what was the first point we put on our parent function for log base 2? What's our first point? 1, 0. Then what was our second point? 2, 1. And then we had, what else did we put? 4, 2, right? We only needed those 3 because we can't put 8 on here. It won't fit. All right, so we need to make that transformation. So if I need to shift to the left, who is changing? The x's, right? So that means to each one of my x's, I am subtracting 4. So what's going to be my new table? What is 1 minus 4? -3. What is 2 minus 4? And then 4 minus 4 is 0. So we have 0, 1, and 2. Why are these staying the same? Did we change our y's? It just affected the x, okay? The other thing to point out from here, from our original, we had a asymptote at x equals 0. So if I'm shifting to the left, what is that going to do to my asymptote? Change it. It's also going to shift with me, right? So where's my new asymptote at? What's 0 minus 4? At -4. So our graph is going to be 1, 2, 3, 4. So here's my asymptote. Oh, whoa, whoa. And we're graphing -3, 0. We're graphing -2, 1. And we're graphing 0, 2. I guess, and technically we could put in 4, 3. There we go. And now we're going to do our best to connect the dots. And there's our transformation. Okay. Do you have to make the table if you don't need it? No, the table is just a tool to help you if you need to see it mathematically, visually happening. Okay. On y2, which transformation variable are we given? There we go. We're given our vertical. So that's our D, and D equals 4, which means we're going up, right? Okay. This time on my parent function, who's changing then? The y's. So my x's are going to stay the same. So I still have 1, 2, 4, and my asymptote is still at 0. But what are my new y's? 0 plus 4 is 4. 1 plus 4 is 5. And 2 plus 4 is 6. Yes, so we're still using our parent function because it's still log base 2, right? We're on the second one, identifying our transformation. So on this one, this transformation, so for y2, you're still at x equals 0. We're now at 1 is 4. 1, 2, 3, 4. We're now at 2 is 5. And 4 is 6. And our asymptote is unchanged because your asymptote only changes if your x changes, because it's x equals. So here's our y2. Here's our y1. If you had a hard time seeing the difference between a horizontal and vertical shift, do you see it now between the two logs? Yeah. Exactly. And then sometimes could they be combined? Could I have one function where I'm going to go to the left and shift up? Yeah, that could totally happen, right? So the x values from here and the y values from here can also make a whole nother graph, right? Because you could have both happening. You can change your x and change your y at the same time.
Okay, if you have both happening,
It would look like the y2, but shift it to the left. And our parent function? Oh, yes. Yes, so if this was a combined, like you said, it will be log base 2, x plus 4 plus 4.
okay.
That would be combining, and so when I combine all the changes to the x that happen here and all the changes to the y's that happen here would merge together. And that would be one function, huh? It's affecting your y and your x. And so therefore also your asymptote would have to move 2. Okay, so if it was one big one, it would create a whole shifted. Okay, all right, transformation exponent with log. Good. Okay, all right, let's work backwards. Okay, so I'm telling you here that I know yours isn't in color, but in mine the red is the parent function. So the red is your parent function, your PF, and I want to write the equation for that. What is the parent function? Good job. Why?
Because the V is on the.
Good job. All right, it is log base 3 of x because what is the value of your x when y is 1? 3. So you know that it's log base 3 of x is the parent function. Bless you, by the way. So then the blue is our transformation. And what do? We reflect it. So how can I make this function reflect? There we go. Our a is negative. We're going to put a negative in front. And what happens? Bam. It reflected. Exactly. So if it not only reflected, then it would also have a value greater. Yes. Visually, it would be your y value getting bigger. So like if I was at 3,1 and there was no anything else, if I was a stretch, then this would have become like 2. Like it would have been 3,2 instead of 3,1. I would still be at 3, but I would have stretched up to 2. Does that make sense? So then it would have been a stretch. Okay. All right. So that's logs. That's B, log base B, and common log. All right. After that, we're going to talk about word problem, and hopefully we're okay with that. Okay. There are 5 steps to solving a word problem. Step 1 is to read. Step 2 is to mark the text. Okay. Step 3 is to identify your variables. Okay, and then step 4 is to plug in variables. So to use the variables, we're going to do it together. Just wanted to make sure we know our steps. And then step 5 is going to be to solve. Okay, I'm going to write it up higher. Put my 5 a little higher. 5 is to solve. All right. Who wants to read? Anybody? I can read. Oh, we're gonna read with an accent? Okay. Not me, but I'll read. The profits in dollars from subscriptions to a local newspaper are shown by the formula P of X equals negative K plus 60 log base 10 of X, where X is the number of subscriptions sold and K is a constant. Find K if the newspaper makes a profit of $35 from selling 100 subscriptions. Okay, so we read, now we're gonna mark the text, okay? Marking the text means I'm gonna go back through and identify key information, right? So an equation is pretty important, right? So we know we have an equation, and then identifying what the values of the equation. We know that X is your number of subscription, K is your constant, and we're going to circle what we're looking for. It wants us to find what? K. And then it tells us that our profit is 35 after we sold 100 subscriptions. So I've now identified all the key parts of this. There we go. So P is what? P is what? P of 100? No, your profit is 35. What do you ask? Oh, when we get to, we haven't plugged in the variables yet. You confused me. I was like, what are we doing? All right, identify our variables. Our variables that were given, we have that profit of 35. So we know that P equals 35, selling 100 subscriptions. Which variable represents subscription? X. So we know X equals 100. Now we're going to plug in what we have. So plugging it in, we know that P of 100 equals 35, which equals negative K plus 60 log base 10 of 100. And now we're going to solve.
Did you put equals log base 10?
Plus, all right, remember a log is asking you 10 to what power is 100? Yes.
Okay.
10 to what power equals 100? That's what log is asking you. 2, right? Because 10 squared is 100. So therefore, what does that equal? 2. So now we have 35 equals negative K plus 60 times 2. So we took something that was algebra 2, and now it's middle school math, right?
Is it times 60 or plus?
It's negative K plus 60 times 2. And what do we need to do to solve for K? Okay, so we're going to first multiply, and we get 35 equals negative K plus 120. Okay, my 2 got weird. All right, what's next? We're going to subtract. Okay, if you owe me $120 and you give me 35, you still owe me how much? Still owe me 85. Okay, what happens when we have a negative on both sides of the equal sign? You can divide or multiply, but either way, what are they going to do? So what is our K? Positive 85. So our constant is 85. Okay, now it's just the constant so that the formula can work every single time. So now that I have the constant, if someone wanted to know, well, what if I sold 200 subscription? How much profit should I make? Would I be able to tell them? Yes. I would just plug it in because I now have my K and I can calculate everything else. Okay. All right. So again, word problems. They are usually mathematically not the hardest of the test, but you have to be patient and be willing to read and mark the text and identify your key information. Okay. Yes. But the math is not hard. You got to be willing to get to the math. Okay.
Really, word problems, it usually be like more than one step in it, and I only do one, and that's what gets me a lot of time.
Yeah.
And then they'll always have the answer for that one step that you did.
Because they like, ooh, let me think like a student. Yeah. They get you. All right.